Let's do it. So today we're going to be starting in on our second unit of the semester with Chapter 3. Your exams you will see next week. All right, but show's got to go on here, right? So we're going to introduce this next topic of alkanes. So what the heck does that even mean? Okay. We're going to actually, before we dive into what exactly alkanes are, we're going to introduce this and the other functional groups that we're going to be studying this semester. All right. The only thing that we need to be able to do is to spy these functional groups for now, and then throughout the semester we'll take one and we'll pick it apart. We'll talk about reactions and how to name them and all that sort of stuff. But now we're going to introduce these various functional groups here. Okay, so in organic chemistry we divide our molecules up. We group them into ones that have similar functional groups, these groups of atoms. And that's because molecules that have these similar functional groups have same sort of reactions and properties, right? So it's a very useful way to categorize molecules in organic chemistry. So functional groups are just groups of atoms in a molecule that share similar properties. All right, so our first functional group is the topic of this chapter, alkanes. An alkane contains only carbon and hydrogen and has all single bonds. Okay. So we've already been drawing a bunch of these, right? In lab, we've been using hexane as a solvent quite often. So that's the structure of hexane there. That would be an alkane, right? Carbons and hydrogens, no other atoms, and all single bonds. Okay. An alkene. This is a molecule that contains only carbons and hydrogens, but has at least one double bond. Right? So if it's all single bonds, we call it an alkane. If there's at least one carbon-carbon double bond in there, we would call it an alkene. Wait, did I mess that up? If it has all single bonds, it's an alkane. If it has one carbon-carbon double bond, it's an alkene. Right? So an example would be if I just take those same 6 carbons, but now throw a double bond in there.
I have a question.
Yeah.
The alkane, so is our first functional group. Is alkene a second functional group, or is
it is a different functional group, yes. All right, and then if the molecule contains a carbon-carbon triple bond, we have another name for those. Those are alkynes with a Y. So again, contain only carbons and hydrogens, but have at least one triple bond. Right, so an example would be something with a triple bond. Remember that we draw about those triple bonds in a linear fashion here. So this would be a 6-carbon alkyne here. All right, and notice that our suffix is changing, right? Alkane, A-N-E, alkene, E-N-E, and alkyne, Y-N-E. All right, so now let's start throwing some other elements in there. An alcohol contains an OH group. All right, so we will often represent these sort of any molecule with an OH group with this R format here. This R simply means any number of carbons and hydrogens. All right, so if you have an organic molecule, a bunch of carbons and hydrogens, and sticking off of one of those carbons is an OH group, we would call that an alcohol. All right, an example of an alcohol would be ethanol. And this is the molecule famous in beer and wine and other such alcoholic beverages. Okay, so an alcohol is necessarily going to contain that OH group, right? There's another similar molecule that contains oxygens called an ether. All right, but the big difference is that the oxygen is going to be bound to 2 carbons. So instead of having a hydrogen on one side, it's going to have a carbon on both sides. All right, so it's like an oxygen in the very middle of a molecule. All right, one example would be diethyl ether. This molecule here, right? We have these 1, 2, 3, 4 carbons, and this oxygen is right in the middle, single bonded to 2 of those carbons. All right. And ethers might be kind of hard to remember, but if we just look at this molecule here and we draw a little face on it and some buck teeth, it becomes the ether bunny. The little ears. Okay? But yeah, so both alcohols and ethers contain oxygens. An alcohol necessarily has a hydrogen bound to that oxygen, whereas in the ether, it's between 2 carbons. All right. An amine is a functional group that contains nitrogen. All right, single bonded to at least 1 carbon. Okay, so what makes amines a little bit different, like with our oxygens, we distinguish between alcohols and ethers. For amines, we don't sort of have that same distinguishing factor here. So for example, this with 1 carbon nitrogen bond is an amine. So is this with 2 carbon nitrogen bonds. And lastly, if we have nitrogen with all 3 of its bonds to carbons, all 3 of these are examples of amines. Okay, so it doesn't matter if it's on the end or in the middle. If it's got a nitrogen and single bonds, we call it an amine. We saw amines in our acid-base chapter quite a bit, playing the role of a base. That nitrogen is really good at accepting a proton, and so that's often what we see in our organic chemistry reactions, is them playing the role of bases. All right. A functional group that's a little bit more rare, less common, is what's called a thiol. This is analogous to an alcohol, but with sulfur instead. So an SH group. Okay, note that sulfur lives just below oxygen on the periodic table. Right, so 2 bonds and 2 lone pairs. So again, sort of analogous to an alcohol group here, but with sulfur instead. That's a thiol. Again, fairly rare, although do play some critical roles. One of our 20 amino acids that make up every protein in our body contains this thiol group here. So it is still fairly important, although not quite as widely seen as alcohols and amines. And then lastly, anything that contains a halogen is what we call an alkyl halide. Right? Halogens often get represented with X, where X can be either fluorine, chlorine, bromine, or iodine. All right, and then the last three that we want to be able to recognize all have one very important bond that we will see over and over and over again in organic chemistry, and we've already seen quite a bit, and that is this carbon-oxygen double bond. Okay? This bond right here has a special name. This is what's called a carbonyl bond. All right. Yes, you can have carbon double bonded to, say, a nitrogen or a sulfur. You will not see that even close to as frequently as you will see this particular bond right here. It plays kind of an outsized role in organic chemistry as well as biochemistry. All right, so there are three functional groups that contain this carbonyl bond here. The first is an aldehyde. Okay, and an aldehyde's distinguishing factor is that it has this carbonyl group, but there's necessarily a hydrogen bound to that carbonyl carbon. So hydrogen bound to carbonyl carbon. So if we draw the structure of an aldehyde, how they look is you will always have that carbonyl carbon at the end. That carbonyl bond is on the end of a molecule, on a terminal carbon. All right, this is different from a ketone. Where you have that carbonyl bond in the middle of a molecule. All right, so an example of a ketone would be the chemical we use to clean our glassware all the time, acetone. Has 3 carbons, and that middle carbon has that carbonyl bond. All right, so again, an aldehyde, the carbonyl bond is at the very end of the molecule. A ketone, it's sitting somewhere in the middle. Truthfully, there's no good reason why they distinguish between these two. They always behave the exact same, but I didn't make the rules, and that's what they have, the organic chemistry gods have decided, is that they're going to fall into 2 separate categories. All right, and then the last one is one that we also saw in our acid-base chapter quite a bit, what's called a carboxylic acid. All right, and that is where our carbonyl carbon is bound to an OH group. Right, they get this name, carboxylic acid, because those protons are readily donatable, because that oxygen's then going to be stabilized through resonance. The conjugate base stabilized through resonance with that carbonyl group. All right, so these are our functional groups that we're going to be studying this semester and that we want to be able to just sight recognize at this point. We haven't really discussed properties of ketones, for example, but if somebody says ketone, we need to know what we're talking about here, right? So flashcard. That's all we need to be able to do right now is recognize them, okay? All right, so our main focus for this particular chapter are these alkanes. That's kind of the simplest type of organic molecule where you only have carbons and hydrogens and only single bonds. So that's kind of a natural place to start. Okay. I will say that eventually a big portion of this chapter is going to be introducing organic chemistry nomenclature to you all. How do we name molecules given their structure? We're going to focus on that next week. That's going to be a big focus for next week. For right now, we're going to just sort of talk about properties of alkanes. Right, so again, alkanes are carbons and hydrogens and all single bonds. Okay, so alkanes, would this be a polar or a non-polar functional group? Non-polar, this is about as non-polar as you can possibly get, right? Only carbons and hydrogens. So this is the epitome of a non-polar functional group. Okay? So because it's a non-polar functional group, what type of intermolecular forces are there between alkanes in solution? Yeah, only those dispersion forces, only those very weak dispersion forces. Okay? Because of that, they have very low melting points and boiling points, right? It does not take very much to break those intermolecular interactions, so they have very low boiling and melting points. Okay? And let's remember that those dispersion forces, they arise from interactions between the surfaces of two neighboring molecules. They're very, very weak, but they're the surfaces of two molecules interacting with one another. So because of that, the more surface area, the stronger those dispersion forces. And so what we see is a trend in our boiling points and melting points, where boiling points and melting points, they increase with increasing chain length. Right, so larger alkanes, just by virtue of having more surface area, are able to form slightly stronger dispersion forces with their neighbors than the smaller alkanes. Right, so for example, if we want to take a look at 3 different alkanes here, we'll take our hexane with its 6 carbons. Methane is just a single carbon. And then decane with 10 carbons. My hexane is too ugly. I got to redo that. Okay. Which one of these is going to have the lowest boiling point?
Okay, out of the 3.
Out of the 3. The A, B, or C? B, right? The one with the least number of carbons, smallest amount of surface area. In the middle would be hexane. Right? And then the one with the highest boiling point would be decane. Indeed, methane is actually a gas at room temperature. its boiling point is negative 70 degrees, right? So you got to get all the way to negative 70 degrees before you get liquid methane. Hexane has a boiling point around 70 degrees. Okay, and then decane is then even more than that, around 170 degrees. The fact that they're all 70s is just coincidence, all right? But yes, point being is as you increase in chain length, the boiling point of those compounds will also increase. All right, and they are primarily used, so alkanes are almost exclusively used as non-polar solvents. So typically when we see alkanes in the lab, they're just playing the role of a solvent, a good, very, very, very non-polar solvent. All right, and that's because they're not all that terribly reactive. There's not very much going on in that molecule other than these very equally distributed carbon and hydrogen bonds, right, where those electrons are nice and evenly distributed. So they're not very reactive molecules, with one enormous exception, which us human beings have taken advantage of almost to a fault in producing energy and thus a huge amount of carbon dioxide, and that is combustion reactions. So most notable reactions: combustion reactions. So when you go to the gas station and you fill up your car, you are just pumping that gas tank full of a whole bunch of alkanes, okay? Which then your car takes advantage of by combusting them. So an alkane plus oxygen gas will generate CO2, H2O, and a crap ton of energy. There's a huge amount of energy that's released in these reactions, which is again how we've taken advantage of them to power the lights in our vehicles and a whole lot of other stuff for the past 100, 150 years. All right. So we're going to use this sort of topic of alkanes to introduce a new sort of structural feature here. All right. So let me actually grab a model kit. All right, so let's say that we were going to draw a 3-carbon alkane. We would do our little zigzaggy line. Right? And if we wanted to draw another carbon coming off of that middle, a branch point here, we would draw it like this, right? Well, that's kind of a little sloppy in terms of the geometry of that molecule, because as it's drawn here, all these bonds are 120 degrees from one another, right? But that's not the structure of my carbon, right? Because my carbon is what? What's that middle carbon? What's the hybridization? Right? So don't forget about that implicit hydrogen that's on there as well. So there are 4 bonds on that carbon. So this is an sp3 hybridized carbon. Those bonds are not 120 degrees apart. That is a tetrahedral shape. So if I were to hold this 3-carbon molecule in my hand, that bond sticking off of that middle carbon is not pointed outward. It's kind of sticking up, right, in that tetrahedral sort of geometry. So in order to represent that more accurately, we're going to use these dashed and wedged bonds. All right, so a wedged bond, by that I mean this bold triangle looking bond. All right? So what that bold triangle is representing is a bond that is sticking out of the page, that's pointing up at you, right? Just like my model kit here, that bond is sticking up in the air, it's pointing out. That's what those wedges represent, a bond that's sticking up out of the page, pointing at you. Okay? Our normal straight flat bonds, right, our normal just sticks here. These are bonds that are in the plane of the page, right? So I have my molecule here, my 3 carbons. Those 2 bonds that sit flat in my hand, they're represented by those normal sticks. Right, so the normal sticks, these are bonds in the plane of the page. All right, and then lastly, we have these dashed bonds. Okay, so another triangle, but instead of being filled in, it's just left kind of with these dashes. These are then the opposite. They are pointing into the page, right? So if I flip my molecule over, I have a bond pointing down, right? Here's the page. I have a bond pointing into the page. That's represented by these dashed bonds. All right, so we're going to introduce these dashed and wedged bonds. We're going to learn how to do something with it called a Newman projection. They are going to be very important in the next chapter as well, or I guess actually 2 chapters from now when we start talking about stereochemistry. All right, but the whole purpose of the dashed and wedged bonds is just it better captures the geometry of what an alkane actually looks like. That's not to say that you won't see something like this. It's just kind of lazy, and it doesn't necessarily contain all the information about how those things are arranged. So we can get away with this sometimes if we don't really need that much information, but there are other times where we really need to know the direction that everything's pointing, and that's why we would use a dashed or a wedged bond. All right? So now we're going to introduce Newman projections. So, Newman projections. It's just another way of drawing structures of organic molecules, but it's a way of drawing structures of organic molecules specifically when we want to see how things are distributed around, how our bonds are distributed. All right, so let me just show you what I mean here. We're going to take this molecule here. All right, we're going to put a wedge on there. We're going to throw a bromine on the other side of that. Okay, and we're going to draw a Newman projection for this molecule that's looking down this bond right here. Right, so it's as if I'm taking this molecule that I just drew. I have my butane with the bromine sticking out of the page. Right, and I'm going to take it and I'm going to turn it and I'm going to look at it this direction, down this bond right here. Okay, so all of your Newman projections are going to have kind of this same basic structure. So let's draw that in first, and then we'll show you how to decorate it. So you're going to draw like a little Mercedes symbol thing, where you have 3 sticks spaced 120 degrees apart. Okay. Then we're going to draw a circle around the middle. All right, and we're going to draw 3 more lines sticking off of just the circle in the back that are kind of staggered with our other ones. So everybody take a second and get this. This is sort of the shell of this Newman structure, that Newman projection that we're going to be filling in here. Okay? So again, I'm looking down this bond here. So this first carbon that I'm looking at, that's located in the very center of my triangle there. All right, I'm looking down that bond. That very middle point there is that carbon. Now, if I'm turning and I'm looking down this bond, the other carbon is directly behind it, right? So that carbon directly behind it is what I'm representing with the circle. So the carbon in front is that midpoint. The carbon in the back is the bigger circle. All right, so then these 3 bonds coming out from the middle, these are the bonds on the front carbon. And these 3 bonds that are attached just to the circle are the bonds on the back carbon. Okay? So if we look at those bonds on my front carbon, I have this, the very first carbon, I'm going to color in blue here. If I'm looking down that bond, that blue carbon is sitting on the top, right? This would be the location of that blue carbon. We're going to use that condensed structural formula format for that, right? So this is a carbon with 3 hydrogens, so we're going to put a CH3 up at that top bond. All right. These wedged bonds, they're pointed out of the page, right? So we need to make sure. So I got these 2 other positions on my red carbon. All right? But that bromine is going to be in one particular position because it's on that wedged bond. The wedges will go on the right-hand side of your diagram. Okay? So that means that bromine will go in the bottom right corner. For the sake of this example here, let's put a dashed bond in on our orange carbon. Put a chlorine on the other side. Remember that dashed bond means that it's pointing into the page, so it's pointed in the opposite direction of our wedge. And those will appear on the left-hand side of your Newman projection. All right. Should I put that chlorine on the bottom left or the top left? Why the top left? Because it's on the one behind it. It's on that orange carbon, right? So my chlorine is going to go over here. All right, and then to fill this the rest of the way in, what else was bound to that red carbon that I just don't explicitly draw in my bond line structures? A hydrogen, so I need to put a hydrogen over here. Same thing on my orange carbon. There's that implied hydrogen pointing in the other direction. And then lastly, to finish this off, I have this carbon that's going to be pointed down, this methyl group, this CH3, off of my back carbon. All right, and so we'll see here in a minute why we like these Newman structures, what they're going to be really useful for portraying, but for right now, let's just make sure that we can draw them. All right, so I'm going to give you a molecule, and you're going to draw me the Newman structure of, or the Newman projection of that molecule. Okay. All right, so again, start by drawing that shell of that Newman projection. Your 1, 2, 3 line, little Mercedes symbol thing. Draw the circle in the middle, and then those 3 lines sticking off of the circle. All right, and again, same idea. You're going to give me the Newman projection of this molecule looking down that C2-C3 bond. See if you can't fill in that Newman projection with the proper labels. All right, so where's this very first carbon in my Newman projection? The very middle. And the one right behind it is represented by the circle. Okay. So then what about this carbon up top on my red carbon? Where should that go? This blue one. On the very top. All right. Now I have another carbon on a wedged bond there. So where should that go? Left or right for the sorry, it's not a wedge, it's a dash. Left or right for the dashes? On the left, is it going to go on the top left or the bottom left? The bottom left, because that's the one where the red carbon is. So that's another methyl group there. Okay. I'm going to fill in my hydrogen that's also attached to my red carbon. Moving on to my back carbon, there's a fluorine on a dashed bond. So that's going to go where? Yeah, top left. All right. And then lastly, where does this very last carbon in my structure go on my Newman projection? The very bottom. All right, and then to fill in that missing hydrogen on my orange carbon. All right, and let's just say that this was a longer molecule. It didn't just have 4 carbons here. There was another carbon sticking off of there, right? In terms of your Newman projection, you would just add the condensed structural formula, CH2CH3. You're only ever looking down one of those bonds, right? So these 2 carbons here sticking off of that orange carbon, I would represent in that condensed formula CH2, CH3. All right, so then just another one. Okay, draw me the Newman projection looking down this bond right here. All right, so this front carbon here is again that very center point. I don't have any dashes or wedges on that, but I do have these two carbons here, right? And I'm going to express this whole group as sticking off the top, CH2, CH3. Since I don't have any dashes or wedges, what am I going to put on my other two bonds? Hydrogens. All right, so then I move to my back carbon, and now I have both a dash and a wedge on there. That's perfectly legal. There's nothing illegal about that, right? It's just showing you how those two bonds are spaced out. The chlorine is pointing into the page, and that alcohol group is pointing out of the page. So which side should the chlorine go on, left or right? On the left. That alcohol group then goes on the right. And what am I going to put on the very bottom? I got to do both of these carbons here, this whole group, my CH2, CH3. All right. So we're going to see these Newman projections in the next chapter as well. Again, they sort of show you the distribution of these bonds. In this chapter, what we're going to do is we're going to use them to do what's called a rotational conformation analysis. Okay, and actually before we move on, let me just say, right, this molecule here I built with my model kit, and I can see that I built it with my bromine sticking up and my chlorine sticking into the page, and if I take it and turn it, I can see that it looks just like my Newman, I deleted these bonds. I can see that it looks just like my Newman projection here. Your model kits can be really helpful. Holy cow, jumping all over the place. All right. If I look down this bond here, I see my methyl group on the top, my bromine on the right, my hydrogen on the left for my front carbon, and then I see my chlorine sticking out on the left, my hydrogen sticking out on the right, and my methyl group pointing down for my back carbon, right? So your model kits are really helpful for these sorts of things, especially when we get to chapter 5. I feel like a model kit's kind of essential, all right? Just in terms of the sort of structures that we're gonna be trying to analyze. All right, so this rotational conformation analysis, what the heck does that mean? So first of all, whenever we draw butane, a 4-carbon alkane, we always draw it like in this little zigzaggy form. That's kind of like the default way of drawing your alkanes, okay? But we talked about how, you know, you can rotate about single bonds. So I could also draw butane like that, right? But why don't we ever see it like that? Okay, that's just a different rotational conformation. All I did was take my butane, right, and I went from being that zigzaggy form, I just rotated about that single bond, and now I get this new structure. All right, but you will like never see it drawn like that. So why? It turns out that this is a way more high energy conformation than if it's in that sort of bent structure like this. All right, and that's what we're going to sort of establish here. Before we move on, everybody take a second and draw me the Newman projection of butane, looking down that C2, C3 bond. Okay. All right. So this carbon that I'm staring at is the one right in the middle. I have this methyl group sticking off of that red carbon, which should go where in my Newman projection? Up at the very top. I have my back carbon represented by that circle, and then that methyl group on that back carbon should be where on my Newman projection? At the very bottom. Right? So we see that all of these bonds are staggered from one another. This is what we call a staggered conformation. And my methyl groups are pointed on opposite sides. Those CH3s are on opposite sides. Okay? So this is what we call a staggered conformation. All those bonds are equally spaced. Okay? And with my methyl groups on opposite sides, this is the lowest energy rotational state of that molecule. All right, so now we're going to take that back carbon and we're going to rotate it 60 degrees. We're going to rotate about that single bond 60 degrees. Okay, so nothing on my front carbon is going to move. Still going to have my blue methyl group sticking up. I just rotated the back carbon. So for my front carbon, I got that blue methyl group up top and those hydrogens on the bottom. But now that back carbon has rotated so that my bonds are in an eclipsed conformation, right? Where they're parallel to the front carbon bonds. Okay, eclipsed conformation. So to be clear, I took my butane, I took this back carbon, and I've rotated it 60 degrees, and now the bonds on the front carbon are parallel to the bonds on the back carbon. Okay, this is what we call an eclipsed conformation. And this is bad. This is higher energy here. Okay? It turns out that if you have a hydrogen-hydrogen bond in this eclipsed structure, it's going to come with a 4 kilojoule per mole energy penalty. All right, those bonds are 4 kilojoules per mole higher energy than our staggered structure. If you have a hydrogen methyl group that's eclipsed, that's even worse. Now you got a penalty of 6 kilojoules. Okay? So we're going to use this table here to calculate the energy of that structure. We're going to do so in kilojoules per mole. Who uses kcal? Biologists? We're not using that. All right? So if we look over here, we have 3 different eclipsed bonds. One of them is a hydrogen-hydrogen eclipsed bond. So this is going to come with a 4 kilojoule per mole penalty. And then I have a hydrogen methyl eclipsed. This comes with a 6 kilojoule penalty. And what about my last eclipse structure? Which one's that? Also going to be the 6, right? Also hydrogen methyl. So this is going to be another 6 kilojoule penalty here. So total, compared to my low energy staggered structure, this one has an energy of 16, I'll keep the same color, 16 kilojoules higher. Okay, so if we make a little plot of energy versus our rotational angle, it's called a torsion angle. We start out with this low energy staggered structure, and then as we rotate, our energy increases to now 16 kilojoules for our eclipsed structure. Right, we started out staggered, we rotated 60 degrees, and now we got this eclipsed conformation. All right, we're going to keep on playing that game. We're going to rotate another 60 degrees. All right, am I still eclipsed? I'm back to a staggered structure now when I rotate 60 degrees. All right, but what's the big difference between this structure and the one that I started out with? Well, is it the same? No, now my methyl group has continued to rotate. So watch what's happening to that back carbon's methyl group, that purple carbon. It is rotating counterclockwise. No, I lied. Clockwise. Okay, so now we're back to another staggered structure. All right. But now these two methyl groups are sitting really close to one another. Right? We're staggered, but those methyl groups are in what's called a Gauss conformation here. If we look at our chart, we have this energy penalty for a methyl-methyl Gauss conformation. It's not huge, right? It's actually less than when our hydrogens are eclipsed. But nonetheless, we're not at our low energy zero state here. Right? So because of that Gauss interaction between those methyl groups, this is now at 3.8 kilojoules. I didn't do a great job leaving myself in any room. So everybody take a second and see if you can't draw me what the structure would look like if we again rotated that back carbon another 60 degrees. All right, what is this thing going to look like now? Take a second and see if you can't tell me what this structure would be if we rotated another 60 degrees. Another sixth of a turn. We get another eclipsed structure, but now those two methyl groups are parallel with one another. Now those two methyl groups are eclipsed in my new conformation here. All right, I'm going to put back up this chart, and I want everybody to take a second and see if they can't calculate the energy of this eclipsed structure here. Anybody got it? 19, awesome, because we have two of these hydrogen-hydrogen eclipsed with a penalty of 4. But now we got this super high energy methyl-methyl eclipsed that has a penalty of 11 kilojoules. So that brings us to a total of 19 for that structure. All right, these are 4 each. And then methyl-methyl eclipsed is 11, bringing us to a total of 19 kilojoules. All right, and if we continued throughout all the different possible rotational conformations, we would see that we get this sort of a graph here. Starting out at our lowest energy conformation, when the methyl groups are on opposite sides of one another, what we call the anti-conformation, right? This is our super low energy staggered conformation. And then as we rotate, we reach one of these eclipsed conformations, which is higher energy. Then we're back down to our staggered structure, but it's the one with that Gauss interaction. So compared to our anti-structure, it's a little bit higher energy. All right, we rotate again to another eclipsed structure where we have that super unstable methyl-methyl interaction. So we get the peak of our little landscape here. Back to our Gauss interaction. Back to eclipsed, and then finally we're back where we started, where our methyl groups are on opposite sides. Okay, so using this chart here, we could predict how that molecule's energy changes as it rotates. So again, why do we always draw these molecules in these like zigzaggy lines? Because that's their most stable structure. They're sitting down here at this energy minimum. Now, to be clear, molecules are still always rotating at all times in space, okay? But the energy of a particular conformation gives you a window in terms of like how much time it spends in that particular state. So this is going to spend most of its time in that anti-conformation, where those two methyl groups are pointed on opposite sides of one another. It'll rotate, but it's not going to spend any time in this eclipse structure here. It's going to quickly move out of that, right? And so that's what the energy, how the energy of this molecule is going to change as this thing is rotating about that single bond. All right, and so for your homework, what you're going to do is take a look at a few different molecules and using this chart here, figure out what the energy is as those molecules rotate about their single bonds. All right, well, that's all I got for y'all.